Okay, now we're on to chapter 16, Chemistry of Benzene, Electrophilic Aromatic Substitution. Alright, so let's just look at what we're going to go. So first off, bromination, other. Alkylation and acylation. What is the difference between alkylation and acylation? I thought an acyl group is adding more rings. Okay, Friedel Crafts. Substitution. Okay. Substituent effects. Tri-substituted benzenes. Nucleophilic aromatic, benzene, oxidation of aromatic compounds, reduction of aromatic compounds, synthesis of polysubstituted benzenes. All right. Why this chapter? This chapter continues the coverage of aromatic molecules begun in the previous chapter, but we'll focus on reactions, looking at the relationship between aromatic structure and reactivity. This relationship is critical into understanding how many biological molecules and pharmaceutical agents are synthesized. And why they behave as they do. In the previous chapter, we looked at aromaticity, the stability associated with benzene and related compounds that contain a cyclic conjugated system of 4n plus 2 pi electrons. In this chapter, we'll look at some of the unique reactions that aromatic molecules undergo. The most common reaction of aromatic compounds is electrophilic aromatic substitution, in which an electrophile reacts with an aromatic ring and substitutes for one of the hydrogens. The reaction is characteristic of all aromatic rings, not just benzene and substituted benzenes. In fact, the ability of a compound to undergo electrophilic substitution is a good test for aromaticity. Many different substituents can be introduced onto an aromatic ring through electrophilic substitution. To list some possibilities, an aromatic ring can be substituted by a halogen, a nitro group, a sulfonic acid group, a hydroxyl group, an alkyl group, or an acyl group. Let me pull up chat. There was actually people in the chat for once. It was kind of nice, actually. All right. Oops. Yeah, actually, I can put it. Maybe that's too distracting. Yes. Okay. Hydroxylation, sulfonation. Nitration. Alright, starting from only a few simple materials, it's possible to prepare many thousands of substituted aromatic compounds. 16.1 Electrophilic aromatic substitution reactions. Bromination. Before seeing how electrophilic aromatic substitutions occur, let's briefly recall what we said in the chapter on alkenes about electrophilic alkene additions. When a reagent such as HCl adds to an alkene, the electrophilic hydrogen ion approaches the pi electrons of the double bond and forms a bond to one of the carbons, leaving a positive charge at the other carbon. This carbocation intermediate then reacts with the nucleophilic chloride ion to yield the addition product. An electrophilic aromatic substitution reaction begins in a similar way, but there's a number of differences. One difference is that the aromatic rings are less reactive towards electrophiles than alkenes. For example, bromine gas in DCM reacts instantly with most alkenes, but does not react with benzene at room temperature. For bromination of benzene to take place, a catalyst such as iron bromide is needed. This catalyst makes the bromine gas molecule more electrophilic by polarizing it to give it an Fe Br4 minus Br plus species. Okay, so there's a catalyst, FeBr3, that works with Br2 to form an FeBr4 minus Br plus intermediate. The polarized bromine gas molecule then reacts with the nucleophilic benzene ring to yield a non-aromatic carbocation intermediate that is doubly allylic and has 3 resonance forms. Okay, so let's try this mechanism. Might as well, right? We have benzene and Br plus minus Br FeBr3. This attacks this and leads to okay. I feel like it's pretty clear what those resonance forms are. Although more stable than a typical alkyl carbocation because of resonance, the intermediate in electrophilic aromatic substitution is nevertheless much less stable than the starting benzene ring itself. Thus, The reaction of an electrophile with a benzene ring is endergonic and has a substantial activation energy and is rather slow. Another difference between alkene addition and aromatic substitution occurs after the carbocation intermediate is formed. Instead of adding Br- to give an addition product, the carbocation intermediate loses H plus from the bromine-bearing carbon to give a substitution product. I see, okay. It's important to see that it really acts as a catalyst and isn't like consumed or anything. Note that this loss of H plus is similar to what occurs in the second step of an E1 reaction. The net effect of reaction of Br2 with benzene is the substitution of H plus by Br plus by the overall mechanism shown here. Okay. So this iron 3 bromide catalyst polarizes the bromine gas so that one is positively charged. Yo, what's up, Ferris? And now the positively charged bromine is electrophilic. So the nucleophilic ring attacks the electrophile. And then the negatively charged iron 3 bromide anion takes a proton and forms a double bond. An electron pair from the benzene ring attacks the positively polarized bromine, forming a CBr bond and leaving a non-aromatic carbocation intermediate. Then the base removes a proton from the carbocation intermediate, and the neutral substitution product forms as 2 electrons from the CH bond move to reform the aromatic ring. Why does the reaction of bromine gas with benzene take a different course than its reaction with alkenes? The answer is straightforward. If addition occurred, the 150 kilojoules per mole of stabilization energy of the aromatic ring would be lost and the overall reaction would be endergonic. When a substitution occurs, though, the stability of the aromatic ring is retained and the reaction is exergonic. An energy diagram for the overall okay, so yeah. So this 1,2 dibromo does not happen. Monobromination of toluene gives a mixture of 3 bromotoluene products. It's probably just ortho, meta, and para. Yep. All right. This looks like a long section, man. All right. Other aromatic substitutions. There are many other kinds of electrophilic aromatic substitutions besides bromination. and all occur by the same general mechanism. Let's look at some of these other reactions briefly. Aromatic halogenation. Chlorine and iodine can be introduced into aromatic rings by electrophilic substitution, just as bromine can, but fluorine is too reactive and only poor yields of monofluoroaromatic products are obtained by direct fluorination. Instead, other sources of F plus are used in which a fluorine atom is bonded to a positively charged nitrogen. One of the most common such reagents go by the acronym FTBF4 in the presence of trifluoromethane sulfonic acid, TFOH. Select fluor. There must be a reason why they're bringing up this, because like we've not done any fluorine chemistry. The major product is the ortho. That's kind of interesting, right? More than 20% of all pharmaceutical agents sold contain fluorine. Really? Well, there you go. Including 30% of the top 100 drugs sold. Sitagliptin, Januvia, used to treat type 2 diabetes. Fluoxetine, I've heard of that actually. Oh yeah, it's Prozac. Fluoxetine, an antidepressant, and atorvastatin, Lipitor, atorvastatin. Bro, these names are crazy. I would hate to have to memorize these freaking names. Whoa. Prozac has a trifluorosubstituted methyl group? That's freaky, dude. Who would have thought that Prozac had a bunch of fluorine in it? That's weird. Aromatic rings react with chlorine gas in the presence of iron chloride catalyst to yield chlorobenzenes, just as they react with bromine gas and iron bromide. This kind of reaction is used in the synthesis of numerous pharmaceutical agents, including the anti-allergy medicine loratadine. Oh, Claritin? No way, that's Claritin? Bro. Kind of looks like an elephant. Okay. Okay, so this also works with Cl2 and FeCl3. Cool. Iodine itself is unreactive towards aromatic rings, such as, iodine itself is unreactive towards aromatic rings, so an oxidizing agent such as hydrogen peroxide or copper chloride must be added to the reaction. These substances accelerate the iodination reactions by oxidizing I2 to a more powerful electrophilic species that reacts as if it was I+. The aromatic ring then reacts with I+ in the typical way, yielding a substitution product. Okay, so I doesn't work with I. So we need either I2 plus H2O2 to form something 2HOI, which is more electrophilic, or I2 plus CuCl2 copper chloride to form I, C plus minus CI. So the mechanism here is we have a benzene ring, and then we have I plus, which is really just iodine gas plus copper chloride, and this gives us the the same thing as I H, and we have a base that comes and takes this and gives us the monosubstituted iodobenzene. Did I want to mention this fluorine thing? We can also fluorinate. We can also fluorinate. Is it anything, or does it have to be toluene? Like, why didn't they show benzene here? It's like sometimes it's like what is it about what they left out? But anyways, so let's just draw this reaction. So we have toluene plus F theta BF4 in TFOH. Just an insane, whatever. But we get F methyl from a 3-to-1 ratio. And this is going to be ortho to para. Okay, that one's pretty easy. Let's get back to the content. Electrophilic aromatic halogenations also occur in the biosynthesis of many naturally occurring molecules, particularly those produced by marine organisms. In humans, the best known example occurs in the thyroid gland during the biosynthesis of thyroxine, a hormone involved in regulating growth and metabolism. The amino acid tyrosine is first iodinated by thyroid peroxidase, and two of the iodinated tyrosine molecules then couple. Two of the iodinated tyrosine molecules then couple. The electrophilic iodinating agent is an I plus species, perhaps hypoiodous acid. Okay, so this thing is called hypoiodous acid that is formed from iodide ion by oxidation with hydrogen peroxide. Right, so tyrosine gets diiodidated to 3,5-diiodo tyrosine. I forget why tyrosine is so important. Tyrosine, something in like cell signaling, I think. I don't even know. Okay, now we got thyroxine, tetraiodate. Okay, all right. That was a little esoteric to me. I don't see why that's useful at all. It's probably useful because they're trying to spell out what are the halogens can we get on to this ring, so that we could do other stuff. But I don't know if does bromobenzene undergo SN2 reactions? What's a good dude, how am I blanking this? A Okay, yeah, like what about, is it CN? For some reason I'm like completely blanking on this. Right, the nucleophile attacks. So we have what are the standard nucleophiles? Right. Oh wait. Oh. Okay, that makes sense. Am I doing a PhD? No, I'm not doing a PhD. Well, I don't know. Not right now. Right now, I'm just like a chud. Um. All right, let's get into this. I feel like this is interesting because these things are explosive. Aromatic rings are nitrated by reaction with a mixture of concentrated nitric and sulfuric acid. I've seen people on YouTube do this a lot, actually. The electrophile is the nitronium ion, NO2 plus, which is formed from nitric acid by protonation. Oh, by protonation and loss of water? That's interesting. So nitric acid gets protonated and loses water to form NO2 plus, which is the electrophile. This is called nitronium ion. Nitronium ion. The nitronium ion reacts with benzene to yield a carbocation intermediate and loss. Okay, so then the benzene alkene double bond attacks, and then we're given a NO2 and then a carbocation. Then what happened? Wait, let's just look at the mechanism. Oh, here we go. I want to draw this. Now this is cool. Okay. So we got HONO minus plus H2SO4. So then a lone pair on the hydrogen's oxygen is there. So then we get this. We get OHN double bond O single bond O plus. This is a minus. And now this comes in, oxygen drops its lone pair, and then this lone pair just goes onto water, and then we form N double bond O plus H2O. So that's the nitronium ion. Then benzene comes in, attacks one of the, it attacks the nitrogen. Yeah, of course it attacks the nitrogen. And then one of the double bonds kicks over. And then this gives us here are the double bonds. This is NO minus plus H. So then water, H2O, comes and takes this proton, and the electrons go back into the system, and we're left with a nitrated benzene, nitrobenzene. And acid. All right, that's pretty neat. Electrophilic nitration of an aromatic ring does not occur in nature, but is particularly important in the laboratory because the nitro substituted product can be reduced by reagents such as iron tin or tin chloride to yield the corresponding arylamine. Okay. Attachment of an amino group to an aromatic ring by the two-step nitration reduction sequence is a key part of the industrial synthesis of many dyes and pharmaceutical agents. Ah, that's interesting. Okay. Iron and acid to base, or hydroxide, and we get aniline. Which is used in many dyes. Okay, now aromatic sulfonation. Aromatic rings can be sulfonated by reaction with so-called fuming sulfuric acid, a mixture of H2SO4 and SO3. The reactive electrophile is either HSO3 plus or neutral SO3, depending on reaction conditions. And substitution occurs by the same two-step mechanism seen previously for bromination and nitration. Note, however, that the sulfonation reaction is readily reversible. It can occur either forward or backward depending on the reaction conditions. Sulfonation is favored in strong acid, but desulfonation is favored in hot, dilute aqueous acid. Okay. Sulfur trioxide. Okay, and then plus H2SO4 sulfuric acid, and we get this reversible reaction where we protonate. So then we get S plus double bond O OH plus HSO4 minus. Now our benzene comes in, attacks the electrophilic sulfur and kicks this lone pair onto it. And then we get phenyl with, H and S, double bond O, single bond O minus, and then plus, and then OH. And then what happens is it's the same thing. It's a base, comes in and takes H and pops it onto the double bond. And then we get, and this is an intermediate, and this goes to S plus double bond O, single bond O minus, OH. And this is called benzene sulfonic acid. All right. These mechanisms are pretty straightforward at this point. Yo, what's up? I don't even know how to say your name, bro. Beh. I'm going to call you Beh. All right. Aromatic sulfonation does not occur naturally. Yeah, that makes sense. But it is widely used in the preparation of dyes and pharmaceutical agents. Okay, so this is also used in dyes. I'm actually curious. My organic chemistry textbook continually talks about the usage of some of these reactions that we learn about in the dye industry, in colored dyes. And is that a big deal? Like the amount they bring it up, it seems like it's a big deal, but I don't hear anybody talking about the dye industry elsewhere. Dude, I feel like it spends too much time on nonsense. For example, the sulfanilamide, were among the first clinically useful antibiotics. Although largely replaced today by more effective agents, sulfa drugs are still used in the treatment of meningitis and urinary tract infections. These drugs are prepared commercially by a process that involves aromatic sulfonation as its key step. Huh. It's a real important industry, but textbooks make it feel more culturally central than it currently seems because dyes were one of the birthplaces of industrial organic chemistry. Interesting. Okay. The dye industry was historically enormous. The first big synthetic dye story was Malvine, discovered by Perkin from aniline coal tar chemistry. It's still a big business, just kind of hidden. Synthetic dyes, about 7 billion. Okay. Yeah, so it's more just about like its context. All right. Aromatic hydroxylation. Direct hydroxylation of an aromatic ring to yield hydroxybenzene or phenol is difficult and rarely done in the laboratory, but occurs much more frequently in biological pathways. An example is the hydroxylation of para-hydroxyphenylacetate. Para-hydroxyphenylacetate. To give 3,4-dihydroxyphenylacetate. The reaction is catalyzed by para-hydroxyphenylacetate 3-hydroxylase. This is a very clever name. No, but it's clear what it does. That's at least, what can you say? I actually really would love to take an enzymes class or something. I mean, I don't know how boring it would be, but it seems like it'd be really cool. And requires molecular oxygen plus the coenzyme reduced flavin. Oh, FADH2. Huh. By analogy with other electrophilic aromatic substitutions, you might expect that an electrophilic oxygen species acting as the OH plus equivalent is needed for the hydroxylation reaction. That is just what happens with the electrophilic oxygen arising by protonation of FAD hydroperoxide. That is OH plus. Mechanism for the electrophilic hydroxylation. Okay. Reduced flavin adenine dinucleotide reacts with a molecular oxygen to a hydroperoxide intermediate. Okay, this mechanism is wonky. Doesn't this get an... What is happening here? Protonation of a hydroperoxide oxygen by an acid HA makes the neighboring oxygen electrophilic and allows the aromatic ring to react. Okay, so this is kind of the first initiating part, and then this is the second part. But shouldn't it be like why is it drawn from the bond? Nah, I don't care. I mean, I just don't get it. But it's fine. Protonation of the hydroperoxy acid makes oxygen. So I'm guessing that this becomes protonated. So it forms peroxide. Then this becomes somehow electrophilic. Bond attacks. And then the intermediate base attacks. Okay, it's pretty simple actually. Propose a mechanism for the electrophilic fluorination of benzene with select fluor. Where was select fluor? This is select fluor. So here's what happens. This thing attacks, or this one attacks. I'm not quite sure about why the meta doesn't show up, but that's okay. And And then this thing or a base just takes the hydrogen, right? I mean, is it not just the exact same thing we've been doing? Yeah, exactly. And then this thing comes into, yeah. All right. So that was not very complicated. How many products might be formed? Oh, wait, actually, is there any? Okay, so it didn't get into why it was ortho and para. How many products might be formed on chlorination of orthoxylene? Metaxylene and paraxylene. All right, so let's just look at orthoxylene. So in orthoxylene, how many products might be formed by chlorination? Yeah, what kind of question is this? So we do this. We do Cl2 and FeCl2, 3. And I don't know where it adds. I don't think they said specifically where it adds. Because all my examples were just with bromine. So then the other one would be the meta. And then finally the para. How many products? Well, oh, I think that 2 can be formed. I think it's more of like a combinatorics, like isomer question, like deduplicate. So in the case of the ortho, there's 2 possible products. In the case of the meta, there's 3 products. And then in the case of the para, I think there's only 1. Okay, so that's my guess. So 2, 3, 1. Let's go. I knew it. All right. When benzene is treated with deuterated sulfuric acid, deuterium slowly replaces all 6 hydrogens in the aromatic ring. What the hell? What the hell is that? All right, I have no idea how to explain that. Okay, let me think about it. Let me look at the sulfonation reaction. I don't understand that. Benzene can be protonated by strong acids. The resulting intermediate can lose either deuterium or hydrogen. If H is lost, deuterated benzene is produced. Attack by deuterium can occur at all positions of the ring and it leads to the eventual replacement of all hydrogens by deuterium. Whatever. That one's kind of a throwaway in my mind. 16.3 Alkylation and acylation of aromatic rings. the Friedel-Crafts reaction. Among the most useful electrophilic aromatic substitution reactions in the laboratory is alkylation, the introduction of an alkyl group onto the benzene ring. The Friedel-Crafts reaction, after its founders, the reaction is carried out by treating an aromatic compound with an alkyl chloride, RCl, in the presence of aluminum trichloride. Or is it just called aluminum chloride? I don't know. To generate a carbocation electrophile, R+. The aluminum chloride catalyzes the reaction by helping the alkyl halide to generate a carbocation in much the same way. Yeah. It also kind of reminds me of like a Grignard. The loss of H plus then completes the reaction. All right, let's look at this mechanism. So, okay, so we have RCl, which is going to be, 2-chloropropane plus AlCl3 forms a carbocation plus AlCl4 minus. Then our benzene ring attacks the carbocation. Move a carbocation. And then AlCl4 minus comes in and attacks. And then we just get our alkylated benzene. And this forms hydrochloric acid and AlCl3. Yeah, this is like the same thing. Despite its utility, the Friedel-Crafts alkylation has several limitations. For one thing, only alkyl halides can be used. How much of a limitation is that really? Aromatic aryl halides and vanillic halides don't react because aryl and vanillic carbocations are too high energy to form under Friedel-Crafts condition. Okay, so caveats to the so this is pre-Crafts. So, aryl halides and vanillic halides don't work because unstable C+. Another limitation is that Friedel-Crafts reactions don't succeed on aromatic rings that are substituted either by a strongly electron withdrawing group, such as a carbonyl, or by a basic amino group that can be protonated. We'll see in this next section that the presence of a substituent group already on a ring can have a dramatic effect on that ring's reactivity to further electrophilic substitution. Rings that contain any of the substituents listed in figure 16.9 do not undergo Friedel-Crafts. Oh, wow. So basically, any of the things that we just learned about, plus even more. Yeah, so like literally anytime there's a substituent on it that's not maybe methyl or like another alkyl group. What about yeah? What about another alkyl group? A third limitation to the Friedel-Crafts alkylation is that it's often difficult to stop the reaction after a single substitution. Once the first alkyl group is on the ring, a second substitution reaction is facilitated for reasons we'll discuss in the next section. Thus, we observe polyalkylation. Reaction of benzene with 1 mole equivalent of 2-chloro-2-methylpropane. 2-chloro-2-methylpropane. For example, yields p-ditert-butylbenzene. Is the major product, along with small amounts of tert-butylbenzene and unreacted benzene. A high yield of monoalkylation product is obtained only when a large excess of benzene is used. Okay. A final limitation to the Friedel-Crafts reaction is that a skeletal rearrangement of the alkyl carbocation, sometimes occurs during reaction. That was the first thing that I thought of, was like, okay, this carbocation that forms is going to be an issue. But I mean, it's also, it's an issue, but it's also an advantage. Treatment of benzene with 1-chlorobutane gives sec-butyl and yeah, that makes sense. But actually, I would expect it to be more. Yeah, okay, so there's nothing new here. If you understand carbocation rearrangements. And here we have dimethyl. Wait, hold on. Yeah, we have an alkyl shift. And then we got the tert thing. Okay. The carbocation rearrangements that accompany Friedel-Crafts reactions are like those that accompany electrophilic additions to alkenes and occur either by hydride or alkyl shift. For example, the relatively unstable primary butyl carbocation. Yeah, okay, come on. This is all by a shift of the hydrogen from C2 to C1. Benzene. Okay, we understand this. This picture is all you need. Just as an aromatic ring is alkylated by reaction with an alkyl chloride, it is acylated by reaction with a carboxylic acid chloride. So this becomes a carbocation that this attacks, and then a base comes and takes the proton. That is an acyl group -C double bond O to R is substituted onto the aromatic ring. For example, reaction of benzene with acetyl chloride yields the ketone acetophenone. This mechanism of a Friedel-Crafts acylation is similar to that of alkylation, and the same limitations on aromatic substrates noted previously for alkylation also apply to acylation. The reactive electrophile is a resonance-stabilized acyl cation. Interesting. Okay. Generated by reaction of the acyl chloride and aluminum chloride. As the resonance structures in the figure indicate, an acyl cation is stabilized by interaction of the vacant orbital on carbon. The acyl cation with lone pair electrons in the neighboring oxygen. Because of the stabilization, no carbocation rearrangement occurs during acylation. See, okay, now this is probably the killer way to mess with benzene. Because before alkylation, what do we do? Well, okay, I mean the main thing is the carbocation, presumably, but I guess the alkylation's pretty good too. What's nice about this one is you can just reduce this carbonyl. You just add. Oh wait. No. How do you remove? Yeah. How do you just remove an alcohol? See, this thing should also have a way to like give what the product is and see if there's any rule that meets it. That would be really cool. How do I take a carbonyl and completely remove it? I know that there is a reagent, and I can't remember what it is. I have to do some serious review. Carbonyl D. No. Oh, this is it. Wolf Kishner. Oh yeah. That's right. It's as azide. Oh, hydrazone. That's right. Hydrazone. What? Oh wait. Let's go back. What? Wait, let me just try NH2, NH2. Oh, there we go. Boom. I knew that there was one that just lops off the... That's a really great reaction. Okay. Okay. All right. So this is Friedel-Crafts acylation. Okay, and we have resonance stabilized carbocation. So we have R C plus double bond O with 2 lone pairs, and R C triple bond O plus with 1 lone pair, plus Al Cl4 minus. So now our benzene comes in and attacks the carbon, and that gives us... Let me draw my benzenes nice. I've been drawing my benzenes so ugly because I've been writing them so much, but it's actually much nicer to have good looking benzenes. And then this is a carbocation, and then AlCl4 minus comes in and takes this hydrogen. Oh wait, this isn't here right now. So I think probably the main thing to remember that's a little niche is that that no carbocation rearrangement happened. But honestly, for that to be asked, it's pretty niche. Oh yeah, plus HCl plus AlCl3. Unlike the multiple substitutions that often occur in Friedel-Crafts alkylations, acylations never occur more than once on a ring because the product is less reactive. The product acyl benzene is less reactive than the non-acylated starting material. Okay, so this acylation only happens once on the ring. Which makes sense because it should be somewhat electron withdrawing with the carbonyl. I would expect this to be slightly electron withdrawing. And I think the list the list has this here. So this carbonyl acyl group. What is an acyl group? Some of these names are confusing. An acyl group is a okay, so something with the carbonyl. I'm not going to dig too deep into that. Okay, here we are. Aromatic alkylations occur in numerous biological pathways. Although there is, of course, no aluminum chloride present in living systems to catalyze the reaction. Instead, the carbocation electrophile is typically formed by dissociation of an organodiphosphate. Did we even do chapter 11? If we did, it might have been in fall. Oh, wait. Fall? Winter. In winter. Yeah, okay. That was a long time ago. I don't remember organodiphosphate. The dissociation is usually assisted by a complexation to a divalent metal cation like magnesium. Okay, bro, that's niche, man. As an example of a biological Friedel-Crafts reaction occurs during the biosynthesis of phylloquinone. Vitamin K1, dude, I was just reading about that today. I think I was on stream reading about that. I asked why are power greens healthy? Human blood clotting factor. Phylloquinone is formed by reaction of 1,4-dihydroxynaphthoic acid with phytyl diphosphate. Okay, this is, dude, I'm not reading all this. This is ridiculous. I mean, it's neat, but, you know. All right, predicting the product of a carbocation. Oh, dude, come on. Come on. If you don't know your carbocation rearrangements yet, you're fucked. Which of the following alkyl halides would you expect to undergo Friedel-Crafts reaction with rearrangement and which without? Which of the following alkyl halides would you expect to undergo Friedel-Crafts with rearrangement? This will not rearrange. This will not rearrange. This will rearrange. Okay, wait, so hold on. Let me just write them down. A, no. B, no. C, yes. D is yes. So this becomes plus. This methyl shifts. Yes, and then this yes. Okay. 16(6). Oh wait, I forgot E. Part E. Chlorocyclohexane. Well, I would say no, but does this one even do anything? I don't know about that one. Cyclohexane threw me for a loop a little bit. What is the major monosubstitution product from the Friedel-Crafts reaction of benzene with 1-chloro-2-methylpropane? Okay. In the presence of, okay, so here we go. So we got benzene plus 1-chloro-2-methylpropane in AlCl3. So this thing goes to okay, I got the product. I think it's just like a tert butyl. What is it called? Tert butyl phenyl? Tert butyl benzene? Let's see. Bruh. It's like, why the... It's like, why did these people try to ruin my life with not having keyboard shortcuts? Tert butyl benzene. Nice. Identify the carboxylic acid chloride that might be used in a Friedel-Crafts acylation to prepare the carboxylic acid chloride? What? Wait, it didn't say anything about carboxylic acids. I gotta look at the answer for 16. Wait, let me check my answers for 6 and 7. All right, terpbutylbenzene. Boom, nailed it. Well, wait, I forgot to do 5. No, no, yes, yes, no. Good. Terpbutylbenzene. Okay, wait. Here's what I want to know. Wait, what is a carboxylic acid chloride? Oh, okay. All right. So wait. So hold on. So ROCl is sometimes called a carboxylic acid chloride, or simply an acid chloride. Okay, that's something that should have been in the textbook because they didn't say that, or if they did, it was not clear. Okay, so anyways, I mean, it's kind of like, yeah, this problem is now do the obvious thing. So we have, so we're gonna have a Cl here, and then the rest of it is easy. So it's gonna be Cl, the bond O. Okay, now let's figure out if I can name this thing. That's probably the most important part, is how do you name it? So let's just name it as if it was a carboxylic acid. Um, I think it's going to be 2-methylpropanoic acid. So then then we'll figure out what So now what I want to know is how do I take this to acid chloride? Isobutyric acid chloride. Is that what maybe I just write this. Isobutyryl chloride. Okay, cool. So this thing is just, so then, or isobutyric acid. I wonder if it stinks. Most of these, I mean, butyric acid smell, honestly, didn't even smell that bad to me. Not even, I bought some, honestly, didn't even smell that bad. It was that it smelled like vomit. I was kind of hoping that I would get a little of that, but I didn't. So this is called isobutyryl chloride. So also 2-methyl propanyl chloride. Is there some alternative names that I can see? Propanoil. Okay, whatever. I don't remember the oil stuff. Okay, now what? Oh, this is called, what is this called? Biphenyl ketone or something? I hate this thing. What am I looking up? I'm looking up what am I looking? Oh yeah, biphenyl ketone. I don't even think that's right. That's interesting. No, because it's not biphenyl. What is this called? Oh, benzophenone. Oh, but this is a special name. Okay, so wait, to do this. Oh, I gotta go to the bathroom. Oh man, this is a long chapter. There's gonna be a lot of resonance drawing forms. Okay, so let's go back up to damn. This is a much longer section than the last chapter. But it's like halfway there. Okay, just give me a second. I'll be back in a sec. Alright, I'm back. And we're trying to synthesize benzophenone by a Riedel Crafts acylation. Oh, acylation. Okay, wait, hold on. So we're gonna have phenol, or no, not phenol. Sorry, benzene. We're gonna react this with um, benzoyl chloride. Hold on, I think low-key I got it. Let's go. Benzoyl chloride. I don't remember the real name with the benzoyl thing, but I do think that that is the right answer. Good stuff. Nice. Okay. Just gotta keep it moving. (16.4) Substituent effects in electrophilic substitutions. Only one product can form when an electrophilic substitution occurs on benzene. But what would happen if we were to carry out a reaction on an aromatic ring that already has a substituent? The initial presence of a substituent on the ring has two effects. Substituents affect the reactivity of the aromatic ring. Some substituents activate the ring, making it more reactive than benzene. Some deactivate the ring, making it less reactive than benzene. In aromatic nitration, for instance, a hydroxyl substituent makes the ring 1,000 times more reactive than benzene, while an NO2 substituent makes the ring more than 10 million times less reactive. Okay, so that's the first effect, is it affects the reactivity of the aromatic ring. Second, substituents affect the orientation of the reaction. The three possible disubstituted products, ortho, meta, and para, are usually not formed in equal amounts. Instead, the nature of the substituent initially present on the benzene ring determines the position of the second substitution. I have to say, as time has gone on, what I used to hate about organic chemistry, I now have a much deeper appreciation for. For instance, it felt really messy. And when you accept that basically the way that this textbook and our collective understanding of organic chemistry was formed was people just tried like a million things, and we had to construct an understanding of what is going on. And it's like pretty wild. So like this whole thing, like in the take away all the context, it just seems like, okay, so what? Like we should you presuppose that we should already have all the answer. But when you accept the fact that, hey, look, someone had to go do the work to figure this thing out, it's a way different story. A hydroxyl group directs the substitution towards the ortho and para positions, for instance, while a carbonyl group directs it meta. Looks experimental results for the nitration of some substituted benzenes. Oh, this is a crazy table, dude. Like, see, this is what I'm saying, is you just do all these reactions and you're like, well, why the hell is this the way it is? It's so weird. Trimethylamine. Wait, why do they say deactivators? Okay, substituents can be classified into 3 groups. Ortho and para-directing activators, ortho and para-directing deactivators, and meta-directing deactivators. There are no meta-directing activators. Notice how the directing effect of a group correlates with its reactivity. All meta-directing groups all meta-directing groups are strongly deactivated. Most ortho and para-directing groups are activating. The halogens are unique in being both ortho and para-directing but weakly deactivating. Oh wait, let's go through this worked example real quick. Predict the major product of sulfonation and toluene. Well, it's going to be ortho, and it's activating. Presumably because it's an electron donating group, right? I don't know. That's my initial feeling. So it's ortho. So we're going to get it. Yeah, ortho para. Yeah. All right. Oof. It's getting late and I'm getting sleepy, dude. Alright, but low-key this video is kind of popping off, so we gotta keep going. Rank the compounds in each of the following groups in order of their reactivity to electrophilic substitution. In order of their reactivity. Okay, cool. I think I got it. So A, we have nitrobenzene, phenol, toluene, and benzene. So then I just go to the table, right? Like, I'm not going to memorize this, am I? So we know that this is going to be... So phenol is 1, toluene is 2, benzene is 3, and the nitrobenzene is 4. That's my guess. Phenol, benzene, benzoic. Okay, so it's going to be phenol, benzene, chlorobenz, and benzoic. So phenol is going to be the most reactive. And I still don't know why. Oh, they're about to get into it. Okay. Then it's going to be benzene. Then chlorobenzene. And benzoic acid. Okay, now we got benzene. Bromobenz. Benz. Ald. And aniline. So what are the activators? Okay, so aniline is better than, wow. Aniline is great, so this is going to be 1. I would assume benzaldehyde, not very good. So then I'm going to say benzene is 2, bromobenzene is 3, and benzal is 4. There's no more. Predict the major products of the following reaction. Nitration of bromobenzene. Wait, hold on. So we got bromobenzene plus NO2. Is that it? Is it just NO2? Anyway, so we go and we look and we see that the halogens are met. The halogens are weakly deactivating, but they go ortho and para. So we're going to get ortho and para. B, oh shoot. And B is bromination of nitrobenzene. Of nitrobenzene. So nitrobenzene is a meta director. So that means that it's going to go right here. So it's going to be phenyl nitrobromine. Okay, chlorination of phenol. So it's going to be activating orthopara. So we're going to get, so C is Cl2 plus FeCl3 plus phenol. And so this is activator ortho. There's no meta directing activators. So it's ortho and meta, ortho and para. Okay, I got it. Bromination of aniline. Aniline is a ortho para activator. So okay, so we got it. Let's just check the answers. So hold on. Phenol, toluene, benzene, nitrobenzene. Phenol, benzene, chlorobenzene, benzoic acid. Aniline, benzene, bromobenzene, benzaldehyde. Okay, here we get orthopara, meta, orthopara, orthopara. Okay. No catalyst is necessary? Oh, wow. Because aniline. All right, I don't need to memorize that, but that's interesting. All right, activating and deactivating effects. What makes a group either activating or deactivating? The common characteristic of all activating groups is that they donate electrons to the ring. Okay, good. Thereby making the ring more electron rich, stabilizing the carbocation intermediate, and lowering the activation for its formation. Conversely, the common characteristic of all deactivating groups is that they withdraw electrons from the ring, thereby making the ring more electron poor, destabilizing the carbocation intermediate, and raising the activation energy for its formation. Compare the electrostatic maps of benzaldehyde, which is deactivated, and chlorobenzene, which is weakly deactivated, and phenol, which is activated, with that of benzene. The ring is more positive yellow-green when an electron withdrawing group such as CHO is present, and more negative red when an electron donating group is present. The withdrawal or donation of electrons by a substituent group is controlled by an interplay of inductive effects and resonance effects. As we saw, an inductive effect is the withdrawal or donation of electrons through a sigma bond due to electronegativity. That's actually well said. Yeah. The withdrawal or donation of electrons through a sigma bond due to electronegativity. Halogens, hydroxyl groups, and carbonyl groups, cyano groups, and nitro groups inductively withdraw electrons through the sigma bond. Wait, hydroxyl? There's something else going on though, because this one's activating. The effect is most pronounced in halobenzenes and phenols, in which the electronegative atom is directly attached to the ring. But it's also significant in carbonyl compounds, nitriles, and nitros, in which the electronegative atom is farther removed. Alkyl groups, on the other hand, inductively donate electrons. This is the same hyperconjugative donative effect that causes alkyl substituents to stabilize alkenes. Yeah, exactly. Zaitsev. A resonance effect is the withdrawal or donation of electrons through a pi bond due to the overlap of p orbital on the substituent with a p orbital on the aromatic ring. The pi electrons flow from the ring to the substituent, leaving a positive charge in the ring. Note that substituents with an electron withdrawing resonance effect have the general structure Y double bond Z, where Z is more electronegative than Y. Conversely, halogen, hydroxyl, alkoxyl, and amino substituents donate electrons to the ring by resonance. I'm low-key, okay. All right, so let me not draw these. But there's a resonance form where this becomes minus, this becomes plus. But in the case where we have like a halogen, we're donating via the pi bond. But in the case of so for halogens, you have inductive and resonance effect. One further point, inductive effects and resonance effects don't necessarily act in the same direction. Yeah, this is what I was trying to understand. Halogen, hydroxyl, alkoxyl, and amino substituents, for instance, have electron withdrawing inductive effects because of the electronegativity of the atom bound, but have electron donating resonance effects because of the lone pair electrons on those XON atoms. When the two effects act in opposite direction, the stronger effect dominates. Thus, hydroxyl, alkoxyl, and amino substituents are activators because their stronger electron donating resonance effect outweighs their weaker withdrawing effect. And you kind of just have to take that as fact. Halogens, however, are deactivated because their stronger electron withdrawing inductive effect outweighs their weaker electron donating resonance effect. All right. Use figure 16.12 to explain why Friedel-Crafts alkylations often give polysubstitution, but acylations don't. Well, because that thing is going to be inductive. It's withdrawing. So it's just going to remove the reactivity. But here with alkylation, you're adding an electron donating group, so it should actually be a positive feedback. You should actually have it like, spam it until you get to steric effects. Let me just read the answer. Yeah. Okay. An electrostatic potential map of trifluoromethylbenzene is shown. Would you expect that trifluoromethylbenzene to be more reactive or less reactive than toluene? Oh, well, given the electrostatic map, it's obviously way less reactive. Okay, ortho and para-directing activators, alkyl groups. Inductive and resonance effects account not only for reactivity, but also for the orientation of electrophilic aromatic substitutions. Take alkyl groups, for instance, which have an electron-donating inductive effect and are ortho and para-directors. The results of toluene nitration are shown. Nitration of toluene might occur either ortho, meta, or para to the methyl group. Giving the 3 carbocation intermediates, all 3 intermediates are resonance stabilized. The ortho and para intermediates are more stabilized than the meta intermediate. For both the ortho and para reactions, but not for the meta reaction, a resonance form places the positive charge directly on the methyl substituted carbon. Oh, okay, I got it. Wait, but this one, oh yeah. Here in the meta, you can't get the carbocation because of the 2 hops. The hops have to be in. All right. So it's mainly about this the fact that the carbocation can be stabilized by the methyl group. Oh gosh. Hydroxyl, alkoxyl, and amino groups are also orthopara activators, but for a different reason than alkyl groups. As described earlier in this section, hydroxyl, alkoxyl, and amino groups have a strong electron donating resonance effect that outweighs a weaker electron withdrawing inductive effect. When phenol is nitrated, for instance, a reaction can occur in either ortho, meta, or para to the hydroxyl, giving the carbocation intermediates shown in a pic. The ortho and para intermediates are more stable than the meta intermediate because they have more resonance forms, including one particularly favorable form that allows the positive charge to be stabilized by electron donation from the substituent oxygen atom. There is both. Well, no, there is a resonance withdrawing effect of the carbonyl, so that there is less resonance donation by the nitrogen. Holy cows. And I never finished the pericyclic reactions either. Ortho and para directing deactivators. Halogens. Is there even a pi system? Like, how does chlorine donate? The deactivators are the strongest of deactiv. Yeah, the strongest deactivators are the meta deactivators. Dude, I'm really losing steam right now. I'm gonna have to review this stuff later. I can't cram any more info into my head. Maybe I'm just gonna like look over my physics practice tests right now. Okay, that's it for tonight. I'm capped.